Okay, so section 1.3 on continuity, end behavior, and limits. So we're going to start by talking about a limit. So a limit can be a difficult concept to understand, especially the way these words in this picture is drawn. So basically what a limit is talking about is checking a function value on a graph from the left-hand side and from the right-hand side to see that it's getting closer and closer to the same value. So in class, I talked about Pac-Man, and if you imagine that Pac-Man is on both ends of this function and he's eating his way down the function, I want to know what value he's getting closer and closer to from the left-hand side and then also from the right-hand side. If I've got Pac-Man going from the right, I want to see what value are they getting closer and closer to as they go across the function. Now the goal is that hopefully whatever the limit is, whatever values they are getting closer and closer to is actually the same as the function value at that point. That's the goal, to show that something is continuous. It would be discontinuous if they are getting closer and closer to different values. Okay? So we're going to look at three different types of discontinuity. So the first is infinite discontinuity, and it's infinite discontinuity when you have an asymptote that is somewhere on your graph. So remember, an asymptote is just an imaginary line that on both sides of your graph it's getting closer and closer to that imaginary line, but it never crosses it and it never actually touches it. Okay, so it's going down to negative infinity on the left hand side and then up to positive infinity on the right hand side. Okay, the second picture would be jump discontinuity. This is actually an example of a piecewise function, and you can see that if I have Pac-Man on this left-hand side, if he's eating up this function, then he's getting closer and closer to whatever this value is. And then if I have Pac-Man on the right-hand side, he's getting closer and closer to whatever this value is, and those are two different values. So that would be a jump in the graph, okay? And it's a piecewise function. And then the third example would be a removable discontinuity if there's a hole in the graph. So it's continuous everywhere except for this one spot. And there's several ways that a hole can exist on the graph, and you're not actually going to be able to see a hole when you graph it in your calculator. You're going to have to use some algebra techniques to figure that out, or look at your table and you might be able to find out where an error might be. So you can see that from the left-hand side it would be getting closer and closer to whatever this value is. It's getting closer and closer to the same value from the right. So they should be getting closer to each other. Just at that one particular point we have an error, or that's undefined. Okay, so to test for continuity, we're going to do a couple of things. First, we're going to check the function value. So I'm going to plug in a number for x and see what that function equals. And then I'm going to check the limit of that function. So I'm going to pick values to the left and to the right of that x value and see what it's getting closer and closer to. If the function value and the limit value are the same thing, then it is continuous. That's great. If there's two different things happening, then we've got to figure out if it's infinite discontinuity, jump discontinuity, or removable discontinuity. So let's look at an example of that. So in example 1, it says to determine whether this function is continuous at x equals 1/2. So to see if it is continuous, first thing we're going to do is plug in our function value. So I want to find out what f of 1/2 equals for this function. So f of 1/2 is going to be 1 over 2 times 1/2 plus 1. Okay, so I'm actually going to use my brain here. 2 times 1/2 I know is 1. So this is 1 over 1 plus 1, which I also know is 2. So 1 over 2 is my function value. Now this is just a coincidence that I plug in 1/2 and I got 1/2, okay? But that is the function value. So the second thing we're going to do is we're going to find the limit of this function. So I'm going to write the limit as x approaches 1/2 of my function, which is 1 over 2x plus 1. And to find out what this limit is, I'm going to draw a table, and my table is going to be horizontal. You can draw it whatever direction you want. It's going to have 2 rows and 5 columns. Now, smack dab in the middle of this, I'm going to put the function value that I already know and where I'm trying to approximate the limit, and that's 1/2. I'm actually going to write it as a decimal, 0.50. And I want to pick values to the left and to the right of 0.5 on the number line, and so I can test those in the function and find out what the limit is. So just a little bit less than 0.50 is 0.49. And then a little bit less than that would be 0.48. Now we're going to go higher than 0.50, so that would be 0.51 and 0.52. So you want to pick numbers just a little bigger and a little smaller. Sometimes you may need to go 3 decimals or 4 decimals. If the values that you're plugging in are just getting repeat decimals, the same thing over and over, then you may have to stretch those out a little bit more. So I'm going to be plugging these into my function, and I actually already have my function typed into y equals in my calculator. Then I can just go to the table and approximate what those values are. And I can show you later on the calculator how to change your settings. So when I look at 0.48 in my table, I get that the value is -25. And then at 0.49, I get -50. We already know that at 0.5, oh, I have the wrong value. Whoops, pause. Let me change my calculator. Okay, that's much better. Very different answers here. I had 2x minus 1 in my calculator. So at 0.48, I have 0.51. At 0.49, I have 0.505, which I'm just going to say is 0.51. We already know the value at 0.5. It was equal to 0.5. And then I have 0.495, so I'm just going to say that's 0.50. And then next would be 0.49. So you can see maybe why I would want to pick and maybe go 3 decimals out. Then I wouldn't have numbers that repeated. I would have more precise answers. So what we're looking here is from the left and from the right, what is this function value getting closer and closer to? Well, I can see that from the left and from the right, both ends of this are getting closer and closer to 0.5. So that means that the limit of this function is equal to 0.5 or 1/2. So that actually means that this function is continuous at 1/2. Now, there might be something going on other parts of the graph, but at this spot on the graph, it's actually continuous. So here's the graph of this function, and this is where we were looking. At 1/2, the value is 1/2. This spot right here on the graph. And so that you can see from the right-hand side, we were getting closer and closer to that 1/2 value. So those were smaller numbers the further we went away. From the from the left-hand side, you see that we had bigger numbers. So those numbers were getting smaller and getting closer and closer to that 1/2 value, or bigger going further and further away. So at this particular point, it is continuous. Now, there is another spot on the graph right here where it would be discontinuous if they had asked us about -1/2. But they didn't. They asked us at +1/2, and it was continuous at that point. Okay, same thing on number 2. We're going to determine if this is continuous and what type of discontinuity there may be at that particular point. Okay, so I'm going to start out the same way. I'm going to find out what my function value is at this point. So I want to find out at f of 1, and we're going to plug in 1 over 1 minus 1. Well, I know that 1 minus 1 is 0, and 1 divided by 0 is actually undefined. Remember, you cannot divide by 0. So we have an issue here. That may be a clue to me that something fishy is going on here. It's not going to be continuous if I have an undefined spot. Okay, so now we're going to look at the limit at this spot. I want to see what's happening to the left and to the right. So the limit as x approaches 1 of 1 over x minus 1. So I'm going to do the same thing as last problem. I'm going to draw my table. And the function value that I've already checked is what's going to go in the middle. So I've already checked at 1, it's undefined. So I want to see what's going on to the left and to the right of 1. So I'm going to go ahead and put this equation in my calculator. I'm going to do 1 divided by, in parentheses, I'm going to put x minus 1. And then I'm going to go to my table, and I'm looking at values around 1. So for example, a little less than 1 I would say is 0.99 and 0.98. A little more than 1 I would do 1.01, 1.02. Again, you can go 3 decimals if you want to. So I'm looking at my table for those values. At 0.98, my value actually equals negative 50. At 0.99, I have negative 100. I can squeeze that in there. At 1.01, I have a positive 100. And at 1.02, I have a positive 50. Okay, so now I want to evaluate this and see what's actually going on. So from the left-hand side, we're getting further and further into the negatives. Okay, so it's kind of getting closer and closer to negative infinity. And then from the right-hand side, we're getting bigger numbers, and so that would be positive infinity. So that's weird because negative infinity and positive infinity are two totally different numbers. Those aren't getting closer and closer to each other. Okay, so we have a problem here that the limit is approaching infinity from both directions. Okay, so let's look at the graph of this one. And again, that undefined in the function value gives me a clue that something fishy is going on here. So if I look at the graph of this function, you can see that at 1, where I was looking, there's an actual asymptote right here. So you can see that as my Pac-Man was approaching from the left-hand side, he was getting closer and closer to negative infinity. But as Pac-Man was approaching from the right-hand side, he was getting closer and closer to positive infinity. So this would be infinite discontinuity. Okay, we're actually going to look at this one. This one's a little tricky too. We want to see at x minus 2 over x squared minus 4 what's happening at x equals 2. So let me go ahead and type this in my calculator, and I would put the whole top in parentheses and the whole bottom in parentheses as well. So first thing I want to do is plug in the function value that they gave me. So I'm going to plug in 2 to this function. So I want to see at f of 2 what's going on. So if I plug in 2, then 2 minus 2 over 2 squared minus 4. Well, I know 2 minus 2 is 0, and I know 2 squared is 4, minus 4 is another 0. So again, we can't divide by 0. This is undefined again. So that tells me something's going on here. Something's not right. Okay, so now I'm going to look at the limit. So the limit as x approaches 2 of x minus 2 over x squared minus 4. So we're going to draw our table. So the function value goes in the middle, 2. We already know that's undefined. Something's going on there. So I'm going to pick values a little less and a little bigger. So I'm going to do 1.99 and 1.98, 2.01 and 2.02. Should have made my table a little bigger. So in my table in my calculator, I actually found this value. So at 1.98, I have the answer 0.25. 1.99, I have 0.25. 2.01, I have 0.25. And 2.02, 0.25. So from the left and from the right, or all the way across, these values are getting closer and closer to 0.25. So that makes me think, which is the same as 1/4, FYI. Maybe I should go back and look at this equation. So I'm going to go up here to the top, and I want to see if I can simplify this equation any, and maybe something's going on here. So I'm just going to do that on top of the word continuous. So on the top, x minus 2 is just x minus 2. I can't do anything with that. In the denominator, this is a difference of 2 squares, and this will factor into x plus 2 and x minus 2. Well, once I factor it, then I notice I have an x minus 2 on the top and an x minus 2 on the bottom that are going to simplify. So that means I would be left with 1 over x plus 2. So this function simplifies to x plus 2. Well, if I go back then and look at my function value, f of 2, at the simplified version of this function, 1 over 2 plus 2, notice that equals 1/4. Okay? So sometimes when you find the function value and your limit, you might want to double check some things, see if you can simplify. So let's look at the graph of this function and see what's going on. Okay, so the equation on here isn't correct. That 4 should be a regular size 4. But you can see on this graph, it is discontinuous over here on the left-hand side, but at the point 2 that we were looking at right here, it's actually 1/4. And we could see that from the left and from the right, it was getting closer and closer to 1/4. Okay, so now we're going to talk about the intermediate value theorem, and this can be kind of confusing if you just use their definition and their picture. So what I'm going to tell you is that the intermediate value theorem is to determine where a 0 might be on a graph. So if on a graph I can plug in a value and I get a positive answer for something and a negative answer for something else, in between those two, it has to cross the x-axis. Okay? Same thing if it was negative and then positive. So I understand these words are confusing, but I'm going to show you in this example what I'm talking about. So this says determine which consecutive integers the real zeros of this function are located on this interval. So what we want to do is we want to plug in function values from -2 to +2 and see what their sign is. We really don't care about the actual function value. I just want to know, is the answer positive or negative? Okay, so I'm going to draw myself a table, and this time I'm going to do a vertical table. Again, it really doesn't matter which direction your table is going. This is just what we're used to seeing. I'm going to split it up into 5 pieces again. And I'm going to plug in the numbers that they gave me from -2, oh, that's nice, negative 1, 0, 1, 2. And I want to find out what the function value is. Really, the number itself isn't important. I'm just looking for sign changes. So at negative 2, the function value is equal to 5.25. Negative 1 is 1.25. 0 is negative 0.75. 1 is also negative 0.75. And positive 2 is 1.25. So again, I'm really not looking at the value, I'm looking for sign changes. So if you notice right here in my table, in between these two values, I went from a positive answer to a negative answer. And then right here in my table, I went from a negative answer to a positive answer. So that tells me on this graph that it crosses the x-axis in between those values. So I would say that between 0 and 1, is that right? Oh, 0 and negative 1. And 1 and 2 is where the zeros are located. Okay, so between 0 and 1, or 0 and negative 1, and 1 and positive 2. So let's look at the graph of this. Hopefully I have the graph up here. So you can see that here is where this graph crosses the x-axis. This point and this point. And if I was just looking at the x values, this is between negative 1 and 0. And this other one is between 1 and 2. Whenever it crosses the x-axis, you're going to have a sign change in your solution. So that just helps us narrow down where the possible solutions are. That's the only purpose of the intermediate value theorem. So don't let the words confuse you on that. So here is another one. I'm going to skip it, but we would do the same thing, plug in values. And you can see right here on this graph, this is where it crosses the x-axis. So that means there's a solution between negative 2 and negative 1. If I did my table, that's where I would have a sign change. But we're going to skip the algebra part on that one. Okay, last thing we're going to look at is the end behavior of a graph. In behavior of a graph, we are looking at the highest exponent. And they don't have that written on here. Oh, let me back up. So we're talking about the highest exponent in an equation. We want to see, is it even or odd? And that's just the number. Is it a 2 or a 3? A 3 or a 5? 6 or a 7? Okay, and then you're going to look at the leading coefficient, which is the number in front of that variable. Okay, we're trying to see what the sign of that number is. Okay, so what I always remember is that if the highest exponent is odd, so that would be an example of like an x cubed or x to the 5th. Okay, if it is a positive x cubed, whatever number is in front of there, then they're going to be doing opposite things, but on the left hand side it's going to be falling, on the right hand side it's going to be rising. Okay, so overall it looks positive. If it is a negative in front of that variable, then it's going to flip-flop. They're still doing opposite things, but overall going to look negative, rising on the right or rising on the left and falling on the right. Now when we look at that highest exponent and it is even, so x squared or x to the 4th, also looking at the coefficient, if it is a positive x squared, it's going to be going up on both ends, so rising and on the left and the right. If it is a negative x to the 4th, it's going to be falling on the left and the right. Okay, so you need to be able to look at the equation and describe the end behavior of that graph. So let's look at this last example. Have x to the third power minus x squared minus 4x plus 4 to describe the end behavior. We're not going to do it algebraically. We're just going to use the rules that I've given you. So I'm looking at this function and I only care about the first term. Nothing else matters, okay? So this first term is odd. Highest exponent is odd. And the coefficient in front of it is positive. So odd and positive. Okay, so that means that overall my graph is going up. So it is actually rising on the right and falls on the left. Okay, and I could graph that. Overall, that's what it would look like. Rising on the right, falling on the left. Okay, here's this graph. So you can see there's stuff happening in the middle. We don't really need to know for this problem what's happening in the middle. I just need to know that on the right it's rising and on the left it's falling.